Welcome to today's tutorial on industrial instrumentation. Today we'll talk about temperature measurement part 9, and the topic that we'll cover here is the miscellaneous methods of temperature measurement. There are mainly 5 miscellaneous methods of temperature measurement, and those are quartz thermometer, solid state thermometer, optical fiber thermometer, ultrasonic thermometer and Langmuir probe, and we'll cover these 5 topics here. The conventional temperature methods as already discussed are the expansion thermometers, which include biomimetic strips filled in thermometers, the electrical temperature transducers like the RTD, thermocouple and thermistor, and the pyrometers, that is optical and radiation pyrometers. Other than these three methods, there are few newly invented techniques that help us measure temperature of process parameters, and these methods come under the head miscellaneous methods. The well-known miscellaneous methods are quartz thermometer, solid state thermometer, fiber optic thermometer, ultrasonic thermometer, and Langmuir probe. The quartz thermometers use quartz resonator wafer sealed in small probes with outer cover of stainless steel to provide additional physical and chemical stability. The quartz surface is deposited with thin gold layer. The case is sealed in a helium atmosphere. It measures temperature by measuring the frequency of a quartz crystal oscillator. The oscillator contains a special cut crystal that results in a linear temperature coefficient of frequency, so that the measurement of the temperature is essentially reduced to measurement of the oscillator frequency. The resonant frequency change is directly proportional to the temperature change. The crystal device is provided with a frequency counter. The crystal's fundamental frequency depends on the crystal thickness. The precise control of the device depends on the crystal geometry and the crystallographic axis orientation. The crystal is provided with the LC cut, while LC stands for linear coefficient. The maximum pressure that these thermometers can withstand is 3000 psi. The temperature measurement range is from -40 degrees Celsius to 240 degrees Celsius with a very high resolution of 0.0001 degrees Celsius, an accuracy of plus minus 0.075 degrees Celsius, and a sensitivity of 1000 Hz per degree Celsius. The quartz crystal's resonant frequency is given by the general equation Ft equal to F0 into 1 plus alpha t plus beta t square plus gamma t cube, where alpha, beta and gamma are temperature coefficients and T is in Kelvin scale. By proper choice of the crystal cutting planes, alpha, beta and gamma can be reduced to 0, and the temperature scale will be a linear function of resonant frequency. The resonant frequency at reference temperature is 28 MHz. The crystal AT cut provides the operational frequency range of 500 kHz to around 300 MHz. The advantages of the quartz thermometer are that the output is highly linear in nature. The device provides very long-term stability and reliability. The device has excellent repeatability with very high accuracy, resolution and sensitivity. The limitations of this thermometer are that it has a slim temperature measurement range. The output gets influenced by changes in the ambient pressure. The solid-state thermometers are simple semiconductor diode and transistors whose voltage or current output changes while operating in the p-n junction forward bias condition due to changes in the surrounding temperature. These thermometers give both current and voltage as output. The voltage output is linear and directly proportional, while the current output is slightly nonlinear. The OM2628 and AD590 ICs give current output, while IC LM35 gives voltage output for the changes in temperature. The measurement range is slender, having a moderate range of -55 degrees Celsius to about 150 degrees Celsius. The working relationship between the voltage and the current and the temperature is given by the following equation. The advantages of the solid-state thermometer are that they are very accurate in measurement, they give significantly high output signal for data interpretation, they are very sensitive temperature sensors. They come at a very low cost. The limitations of these thermometers are, however, they have a very small temperature range and the output response is somewhat limited due to their own thermal mass. The fiber optic thermometer is involved in moderate to high temperature measurement utilizing blackbody radiation principle. The fiber optic thermometer consists of single or multi-fiber bundles. The fiber is made up of gallium arsenide semiconductor crystal. The fiber collects infrared radiation from the hot body and transmits the same to the infrared detector. The detector senses the radiated signal and converts it into corresponding voltage output calibrated in temperature scale. The radiation collected is directly proportional to the temperature of the body under measurement. The fiber thermometer is dependent on either the emitted radiation or the observable brightness of the hot body. The fiber optic is sensitive only to the near infrared to infrared portion of the spectrum and filters out all other parts of the spectrum. The temperature measurement range is from 100 -100 degrees Celsius to about 1100 degrees Celsius. The advantages of the fiber optic thermometer are as follows. The device is a non-contact device and carries out measurement from at a distance. The device size is small and it is rugged in construction. There is no requirement of any line of sight to carry out the measurement. The measurement is not influenced by radio frequency, microwave, electromagnetic field, or shock and vibration. It has a wide temperature measurement range and the measurement is done at a very fast rate. The device is capable to carry out temperature measurement across opaque objects as well. The only limiting factor of this device is that the cost per unit temperature measurement is very high. The ultrasonic thermometer utilizes the effect of temperature on sound wave velocity in the transmitting medium. The thermometer can be used in gaseous, liquid, and solid mediums. The sound velocity is directly proportional for gaseous mediums and inversely proportional in liquid and solid mediums. That is, the sound velocity goes up as temperature increases in the gas environment, but the sound velocity decreases with temperature increase in liquid and solid mediums. The velocity is dependent on the gaseous medium temperature as shown in the equation V square equal to gamma RT by mW. The temperature-dependent acoustic velocity Vt in solid medium is dependent on the material density ρT and its elastic modulus Et as shown in the equation below, that is Vt equal to under root Et by ρT. The acoustic velocity is detected by immersing a rod or a wire into the fluid or by using the medium itself. The measurement is carried out by measuring the time difference between the consecutive sound wave reflections. The device effectively has three parts: thin wire sensor, sound conductor, and transmitter receiver transducer. The thin wire is immersed in the medium and this senses the acoustic velocity. The lead-in wire carries the pulse to the thin wire sensor. The reflection from the beginning and the end of the thin wire provides the necessary time-lapse information. The transmitting transducer sends out the acoustic energy through the medium while the receiving transducer detects the energy and the time delay and determines the sound velocity. When the medium itself is used as the conductor in case of solid, the transducer is located in an external shell. This configuration is useful for temperature measurement in corrosive environment as well. The temperature measurement range of the ultrasonic thermometer is from -270 degrees Celsius to 3000 degrees Celsius. The sensor is made up of materials like thoriated tungsten, rhenium, titanium, platinum, niobium, molybdenum, and sapphire single crystal. The sensor can operate at extreme high frequencies, providing sampling rates in the 1 to 5 GHz range. The advantages of the ultrasonic thermometer are that it is highly accurate with an accuracy of 0.01%. It caters a wide temperature range from the cryogenic levels to the plasma temperature range with slight modifications, that is from minus 270 degrees Celsius to about 3000 degrees Celsius. The limiting factors of the ultrasonic thermometer are that the ultrasonic thermometer is costly, it is highly required to have pressure correction before ensuring the measurement. The UT thermometer cannot be used for point-based measurement. The UT thermometer for gaseous mediums performs with limited response for non-ideal gas behaviors. The sensor requires very accurate specific heat ratio determination. The Langmuir probe is a simple device that is used in determination of electron temperature, electron density, electric potential of plasma, as well as ion temperature and ion density. The probe is capable to measure electron and ion temperature that varies between minus 200 degrees Celsius to about 10,000 degrees Celsius, that is in the plasma range. It works by inserting one or more electrons into the plasma state of matter and is maintained at either a constant or time-varying potential difference between the electrodes and the surrounding vessels. The physical properties of the plasma are detected and determined by having a measure of the potential differences and current flowing in the system circuit. Bomb criteria provides the guiding equation associated with the measurement of the electron properties and is cited below. The Langmuir probe provides simple and inexpensive diagnostic analysis of plasma parameters. The Langmuir probe is essentially a conducting wire placed inside a plasma and has variable bias voltage. The current that flows through the circuit due to this bias voltage essentially has three regions in the IV characteristic curve. Those are electron collector region, electron retardation region, and ion collection region. One very important component of the Langmuir probe is the Debye sheet, which is a layer in the plasma with a greater density of positive ions and hence an overall excess positive charge that balances an opposite negative charge on the surface of the material with which it is in contact. The electron temperature, electron density, ion temperature, ion density, and plasma potential all can be derived from the IV characteristic curve. A probe system can provide the following parameters: floating potential Vf, which is the point where ion collection current equals the electron retarding current. This is the potential at which an isolated object will float when placed in the plasma. The plasma potential Vp is the potential of the space the plasma occupies. It is normally positive with respect to the surrounding chamber to prevent excessive loss of electrons. Below the Vp, the electrons are retarded by the probe potential and the electron current falls off at a rate that depends on the electron average energy. Above the Vp, we enter the electron collection region. It is possible to calculate the electron density, Ne, from the magnitude of the current at the plasma potential. The ion density Ni is determined from the ion current in the ion collection region. Readers can refer to the following links and references for more detailed study. Thank you.